All right, now here we go. Second exam for Calc 2, taken from fall. I know it says spring, but it's the fall exam of 2025. What is this test about? This is about techniques. And really, this is where we say, integration is an art form. And a lot of it is just manipulating. You get a little bit of algebra in there, a little bit of trig, a lot to do. And so this is going to be a good test in that it will really test us. We're going to have 10 problems, 6 multiple choice, 4 workout. And so without further ado, let's get going. Starting with multiple choice, only have to find the right answer. No justification needed. So, number 1. Find the integral of arctangent 4x dx. Now, before we do the problem the way they intended us to do it, let's talk about a way that we could do it, which probably is faster. We won't go through it and fill in all the details, but that is to say, we're supposed to end up with the antiderivative. So what can we do? Well, we can say here are 5 candidates, and just think about take the derivative, and which one would end up with an arctangent of 4x. Some of them, A, B, and D in particular, you can look at those and just roughly see, hey, there's no way I'm getting an arctangent out of there, which only leaves you with C and E. And they're kind of close except for this term here. And if you take the derivative of E, you see you don't get arctangent 4x. So the answer, I betcha, is C. Now that's not how they intended you to do it, but that's a perfectly valid way. So let's talk about the way they intended. All right, so we say, well, arctangent of 4x, the problem with this is what? Well, that's not one of our functions that we know. There's like 10 functions we know how to integrate. This is not one of them. So we say, well, can we do something else? We can differentiate it. Well, that can be helpful. It can be helpful if it has a nice derivative. So we say, but you might say, well, wait, how does differentiating help us? We're supposed to be integrating. So if you're faced with an integral, you say, well, it has a terrible antiderivative because I don't know what it is. That makes it terrible. But it has a beautiful derivative. You say, we can do integration by parts. It says what? Integration by parts says we're going to differentiate a piece and integrate a piece. Now, you might also say, but wait, Steve, there's just one piece here. How can we integrate and differentiate if there's only one? Well, we add this magical 1. We say, all right, we're going to let this part be our u, and this part will be our dv. So what do we have? Well, we have du, derivative of arctangent of 4x. Well, it's 1 plus square that, 16x squared in the denominator, times the derivative of 4x, which is 4 dx. And then the antiderivative of 1 dx is simply x. All right, and as a reminder, I should have written this down. Integral of u dv is uv minus the integral v du. All right, so accordingly, what does this give us? Well, we have uv x arctangent of 4x minus the integral v du. So that's a 4x over 1 plus 16x squared dx. And now we're like, okay, so we've seen x arctangent of 4x, right? Good. And then we have this other piece. And this other piece, well, how do we integrate that? Well, it kind of looks like a log type integral, right? Because you have something downstairs, and the derivative of the downstairs looks very similar to the upstairs. So if you let u equal 1 plus 16x squared, then what do you end up with? Well, we end up with du is 32x dx, or if you divide by 8, 1/8 du is 4x dx. So that this becomes just this piece right here. just that part, is 1/8 integral 1 over u du, which is 1/8 log u. So we have our x, arctangent 4x. That just comes along for the ride. And then we have that minus, that comes along, 1/8 log, and u is 1 plus 16x squared. Toss in a plus c for good measure, and life is good. The answer is C. All right. Whew, that was just problem 1. All right, we have a fun test ahead of us. Number 2. Find the integral sine to the 4th x cosine to the 5th x dx. Now, here we have an integral with just sines and cosines. So there's a couple of possibilities. One of them is that all the powers are even. If that happens, we do power reduction. The other possibility is some power is odd. And that's where we're at here. So if we're faced with the scenario that at least one of the terms has an odd power, we say cool, 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 cool. What we do in that case is we say, let's pull off that odd one. So we're going to get a sine to the 4th x, cosine to the 4th x, and a cosine x dx. See that odd one? I pulled off an odd one to the end. And here's the mindset to have. This cosine x dx, our goal is we're going to make this part become a du. That's the game. Well, what gives rid of a cosine? That says you should better be a sine. So our process, our mental thought process here says pull off the odd one, and then we say, okay, write everything in terms of the other, right? So if you pulled off a cosine, write everything in terms of sine. If you pulled off a sine, write everything in terms of cosine. Be careful, get your negatives right. And we say, okay, well, the sine, that's great, as is, beautissimo. But the cosine we need to fix. And you might say, okay, but why did we pull off from the odd one? So that what we had was an even power, which means this cosine to the 4th is really cosine squared squared. What's cosine squared? It's 1 minus sine squared, right? Because sine squared plus cosine squared equals 1. And that's what happens. We pull off from the odd one and then use this identity. So what do we really have at this point? We have sine to the 4th x, 1 minus sine squared x squared cosine x dx. And now we're ready to begin our substitution. We already talked about u is sine. We already talked about du is cosine. And so we put everything together. What do we get? Well, this is du. This sine to the 4th is u to the 4th. And this is 1 minus u squared squared. All right. So that's u to the 4th. 1 minus u squared squared is 1 minus 2u squared plus u to the 4th. Or, that's the integral, u to the 4th minus 2u to the 6th plus u to the 8th du. And notice, what have we done? We've turned our trig integral into an algebra integral. In particular, a pretty nice algebra one. 1/5 u to the 5th, 2/7 u to the 7th, 1/9 u to the 9th, plus c. And then the last thing is say, well, wait, hold on, but u is sine. I saw the sign, and it opened up my eyes. I saw the sign. No problem's going to keep me down. All right. So we have 1/5 sine to the 5th minus 2/7 sine to the 7th plus 1/9 sine to the 9th plus c. So does anything look like this? D looks a lot like that. And that's the answer. Whew. I will say, trig can be tricky sometimes, because what can happen, and this is, even if you're paying attention, the answer can sometimes be written in different ways. And you can even take different paths to get to it. So you have to be careful. But in this case, there was a pretty clear, laid out path, and they didn't try to do anything tricky with the answer. So nice. Thank you. Thank you for making life good. All right. I will note that there are some fun options. If you notice C, now C may not look tempting now, but where would it come from? Well, somebody might have said, oh, the integral of sine to the fourth, well, that's like a 1/5 sine to the fifth. And cosine, well, that's going to be like a cosine to the 6 times a 6. But then you have a negative. So that might be if like, oh, integrate the parts like that. But that's not how it works. No. Be careful. They throw some tricky answers in there. Try to make sure you're paying attention. But we're paying attention. We're not going to let them get us. All right, moving on to number 3. For x bigger than 3/2, a substitution turns the integral, this integral, 2x squared over square root of 4x squared minus 9 dx, into one of these integrals. Okay, well, what do we have here? Let's think about what's going on. Now, what do we see? We see a square root involved, and there's a plus or minus happening on the inside. Now, that's telling us, like, oh, they're trying to have us channel trig substitution. And the answers are also suggesting that. Notice we start out with algebra, but here we have a lot of trigonometry. So the way we would do that is if we did some sort of a trig substitution. So let's recap trig substitution. If we see a square root of, we'll start with a squared minus u squared, well, that says you should use a sine substitution. If we see an a squared plus a u squared, well, that says we should be thinking tangent. And if we see u squared minus a squared, that is a secant. So, which setting are we in? So you should think of the u as the part with the variable and a as a number. So the variable is in the front. So we are in the u squared minus a squared. So we are thinking secant. All right. Now, that doesn't really rule much out. C, though, I'm pretty confident we can rule that out. That doesn't feel right. So we need to do a couple of things. First off, what is u? What is a? So coming into here, we really have this is 2x squared minus 3 squared. So our u is 2x and our a is 3. So we're going to let 2x is equal to 3 secant theta, or x equals 3/2 secant theta. Okay? All right, so if we do that, we get dx is 3/2 secant tangent. That's going to show up at some point. And so let's put it together what we have. We know what x is. It's 3/2 secant theta. So I'm going to replace this x, right? So we got to see there's like 3 x's. So you got to talk about each one of those. So for the 2 times x squared, that'll be 2 times 3/2 secant theta squared. The dx will be a 3/2 secant theta tangent theta. Okay, that's the dx. And now this 4x squared downstairs, and oops, I forgot to write down a d theta there. I'm so sorry. Well, it's multiple choice, right? Even if we forget a little small thing, we still get credit. All right, downstairs, okay, pace ourselves. We are going to end up with square root of 9 secant squared times, right? So that 2x minus squared is 9 secant squared, not times, and then subtract 9. Okay, let's talk about the downstairs. We can pull out a 9, and if we do that, what do we have? Just this downstairs part. Square root of 9 is 3. Then we get the square root of secant squared minus 1. Secant squared minus 1, also known as tangent squared. So this is 3 tangent theta. And now we're like, cool. This 3 tangent theta, I can knock out a 3 tangent theta upstairs. What do we have left? Well, we have a 3 squared, which is a 9, a 2 squared, which is a 4, times a 2, which is a half, times a half, which is a 4 downstairs, right? Just gathering the 2's. There's a secant squared and a secant, so that's the secant cubed and d theta. So 9/4 secant cubed theta d theta. All right, does anything look like a 9/4 secant cubed theta d theta? B. And there we go. Wow, good, good. Pay attention. Really, it's just knowing what's the right substitution to make is, and then just carefully following through. The only thing that makes this one particularly hard is that, it's not just x squared, it's 4x squared, right? So you have to follow that through, and it's very easy. If you lose that, you may end up with something slightly different. So pay attention. Pay attention. All right. Number 4. What is the general form of the partial fraction decomposition of the function 5 minus x to the 5th over x minus 1 squared, x squared plus 1 squared? And it says, note, you do not need to find the values of the coefficients. Well, of course not, because we just have to pick a through e. Now, we can do this one actually surprisingly fast if you know one fun check. There's a good check with partial fractions. It won't work all the time, but this will help you narrow it down really quickly. That is to say that the number of unknowns, the number of coefficients in your partial fraction decomposition has to match the degree of your denominator. What degree did we start with? An x squared, squared, all told that's x to the 6 downstairs. So we need 6 different unknowns. This has 1, 2, nope, 1, 2, nope, 1, 2, 3, 4, nope, 1, 2, 3, 4, 5, 6, good, 1, 2, 3, 4. So the answer is D. If we know just that fun fact, we get the answer. Now let's suppose we forgot that. Well, what do we do? Now, the decomposition, you don't need to worry about the upstairs. It all comes from the downstairs. So that's where we focus our energy. Don't worry about up here. The only thing you technically have to worry about is the degree upstairs less than the degree downstairs. And if it's not, you do long division, but that's not part of this problem. So this 5 minus x to the 5th, that's a red herring, meant to distract us. And now we say, okay, there's an x minus 1 squared, which means we need to build up to x minus 1 squared. So you're going to have an x minus 1 term and an x minus 1 squared term. Similar, there's an x squared plus 1 squared, so that means we need to build up to x squared plus 1 squared. So you have an x squared plus 1 and an x squared plus 1 squared. Now, what goes in the numerator? Well, focus on sort of the inside piece. Here, x minus 1 linear, that's some constant. X minus 1 is the inside piece, so not the square part, but the x minus 1. So again, a constant. Here, the inside is x squared plus 1. Quadratic, so you need to have a linear upstairs. The x squared plus 1, that's the inside, so it's a linear upstairs. And that matches D. And so there you go. This one is meant to be a quick problem, and hopefully it will be if you see it again, because you will want some time to answer the other ones. All right, moving on to number 5. What is the maximum error given by the formula, and they give it to us? Sometimes they just won't give it to you. You'll say, oh, look at the formula sheet. Whoa. But it's like, here it is. So the error in the trapezoid rule, that's what ET means, is less than or equal to m b minus a cubed over 12n squared. From the trapezoid rule, when estimating the integral 1 to 2 log x dx with n equals 4 and m is the maximum value of f double prime of x on the interval. So we just have to sort of dig into this. We have a couple of things, right? There's the n. We know n. There's b and a. That comes from the bounds. So what we have is a equals 1, b equals 2, and so b minus a is 1. So it's the difference. So where do we need to put the energy to this problem? Well, the energy, our efforts, is really nailing down this m. Say, well, what is m? M is the maximum value of f double prime. Here is f. So we're going to take a look at what is f double prime. So we begin. We have f. Well, that's log. I really should say f of x equals f prime of x, 1 over x, f double prime of x, negative 1 over x squared. So the maximum size of f double prime of x, which by the way is saying 1 over positive x squared, for 1 less than or equal to x less than or equal to 2. Think about how big this can get. Well, if you think about it, the larger your denominator is, the smaller the value is. So we say, aha, the largest that f double prime in magnitude can get is at x equals 1. So we get that m equals 1. All right, now we just tie our pieces together. So we know that m equals 1. b minus a is 1, so we have 1 cubed. We have a 12, and n equals 4, so that's 4 squared. All right, so that's a 1 over 12 times 16. And 12 times 16, that's 160 plus 32. So that's 1 over 192. And that's D. And there we go. All right, so that's as far off as we can be. Now, I will note we can rule some things out. When we talk about error, we don't take negative values, so we could rule out B and E very quickly. And so, if nothing else, a 1 in 3 chance, right? Be reasonable. If you're having a hard time nailing it down, say, can I at least rule out some options really quickly? And if you can, that gives you an advantage. Use every advantage you can. Your goal, maximize your points. Got to get them all, right? But you know what? Got to get as many as you can. Think about how you can do that. Help yourself succeed. All right. We have one more multiple choice problem. Number 6, and here we go. What is the estimate of the value of the integral 0 to 2 of 2x squared plus 3dx using the trapezoid rule and n equals 4 intervals? All right. Well, what would we get? What does the trapezoid rule tell us? Well, there's this nice little pattern. You have the delta x over 2, and then there's this 1, 2, 2, 2. Let's see how many intervals we have. 2, 2, 2, 1, 2, 3. I think it's that many. We'll check. We'll check it in just a second. All right. Now, what is this saying here? Well, what it's saying is you say, do the following. You take your 0 to 2. So here we're marking 0 to 2. And we're going to split it into 4 pieces. So we go halfway. And I will say, on a small technical note, they didn't specify that they were 4 equally sized pieces. They should have. They should have. Now, everybody assumes that's what they meant. But when you're doing numerical integration, you don't actually have to have that assumption. So it should be stated. Okay, but back to our regularly scheduled problem. All right, so we're splitting it. And we say, all right, well, what do we need to do? Well, we have the width of the intervals. There's the delta x. So here, the delta x is a half. So that's our delta x. And now, what we want to say is we're going to weight them. So we're going to weight the endpoints a little bit less than we weigh the middle points. And the reason we're doing this is essentially what happens is we're weighting half and half for this interval from these 2 endpoints. But we're also doing half and half here. And so these 2 halves combine. That's what's going on. But okay, back what's going on to what we need to do. So delta x over 2, we're going to get a 1/4. Now we weigh them. A 1 times f of 0 plus a 2 times f of a half plus a 2 times f of 1 plus a 2 times f of 3 halves plus a 1 times f of 2. Okay, so just to summarize, this 1, 2, 2, 2, 1, that's these coefficients in front. All right, so what do we need to do? We need to do some evaluations. And we just have to be patient with ourselves. And we can do what? Well, it's 1/4. F of 0, this is our f. And if you plug in 0, you get 3. And 1 times 3. So I'll go ahead and put that 1 again. 2 times f of a half. 1/2 squared is 1/4 times 2 makes it a half plus 3. And so it's going to be a half plus 3. Okay, plus 2 times f of 1. Well, that's 2 plus 3, and that's 5. 2 times f of 3 halves. 3 halves squared is 9/4 times 2 makes 9 halves. And then we're going to add 3. Plus 1 times f of 2. 2 times 2 squared, that's 2 times 4, 8, plus 3 makes 11. All right, well, I got to simplify. And what do we get? Well, we get a 1/4 times, if we distribute through a 3, 2 times a half makes a 1, plus 6. 2 times 5 makes 10. 2 times 9 halves makes a 9. 2 times 3 makes 6. And 1 times 11 makes 11. And we start adding these up. 3 plus 1 is 4, plus 6, that's 10. There's 20, 29, 35, 46. So that's 46. And then times a fourth. 1/4 times 46. Well, you can divide a 2 out. 23 over 2. Good. Good. Because that's an option. Nice. Now, one thing you might be tempted to try, it's not a bad thing, but let's just make a comment here. You might say, well, the answer is approximately just do the integral. You say, oh, okay, well, let's just do the integral. Let's see what happens. Well, that would be 2/3 x cubed plus 3x. And going from 0 to 2, well, plug in 0, you get 0. And if you plug in 2, you'll get 2/3 times 8, that's 16/3. And then you get plus 3 times 2 is 6. Well, that's 12/3. And yes, And so that gives us a 28 over 3. And, oh, sorry, not 12 thirds, excuse me. 3 times 2 is 6. That makes an 18 thirds. I can do math. And that makes 34 thirds. So what does that mean? Well, the answer should be really close to 34 thirds, which is like 11 and a third, right? This is 11.333, so forth and so on. And you might say, aha, 34 thirds. So is that the answer? Well, no, 23 halves. So wait a second. 34 thirds is the exact value. Why is it 23 halves? Because the way that trapezoid rule works is you get error. You always are going to get a little bit of error unless you happen to be a nice linear function, which this is not. And so there is, be careful. It's tempting to say, oh, I'll just find the exact answer and look for something that's close. Well, if you do the exact answer, and this is really interesting because 72 thirds, that's 24. You can rule out 72 thirds really quickly, but 34 thirds is close to 11. It's also close to 23 halves. That's 11.5. And 23 over 6, well, that's like 4. That's far away. But yeah, be careful. There can be a gap between the exact value and the approximation. All right. So we're not going to fall for anything like that, right? No, of course not. We're into the workout. And so we've done 6 out of 10. We're doing okay. That means we got about 10 minutes per problem at this state. And here we got to show our work. So we're going to be extra careful. We'll start with number 7. Find the integral 0 to 3 root 3 x cubed over root x squared plus 9 dx. All right, move it up a little bit. What kind of problem have they given us? That's actually a big and very important first step when we're solving these, to say what's the right technique. We see a square root, and specifically we see a square root of x squared plus 9. So oftentimes when we see that, we should say, oh, this probably should be like a trig substitution. Okay, so that's certainly something we can do, and let's try it out. I think we can do it without trig substitution, but let's wait. If we have a few minutes, we'll go back and say, let's try to do it without trig substitution. All right, so what do we have? Well, because we see a u squared plus an a squared, that's suggesting we should have u equals a tangent theta. Or in our case, x is 3 tangent theta. Okay, well, what do we have? We're going to replace all the x's in terms of theta. So integral, and remember the bounds, right? These aren't just magic numbers floating in space. These are attached to the variables. So this is an x equals 0 to x equals 3 root 3. We want to go to theta equals something, to theta equals something. Okay, so we got to update those as well. And so we have a bit of work cut out for us. Let's go through term by term. The x cubed, that'll be the easiest thing to handle. That's 3 tangent theta squared. The dx, well, derivative of tangent is secant squared. So that's 3 secant squared theta d theta. Downstairs, the square root of x squared plus 9, square root of x squared plus 9, well, that's going to become the square root of 9 tangent squared plus 9. And the square root of 9 is 3, so you can pull that out. And then you have the square root of tangent squared plus 1. But now, from our formula sheet, Tangent squared plus 1 is secant squared. And then the square root of secant squared is secant. And that's the whole reason we're doing all of this, is we get something that's a little bit easier for us to digest. Now the bounds. When x equals 0, 0 equals 3 tangent theta. Well, that says that tangent theta equals 0. And that says, hey, that would correspond to theta equals 0. So our old bound, that's our x bound. We're moving to a new bound, a theta bound. Our old bound was 0. What's our new bound? Also 0. But be careful, right? Because now we'll do the other one. 3 root 3 equals 3 tangent theta. Well, that says tangent of theta. That's equal to root 3. And here's a good time to use your formula sheet. You grab the tangent theta row, scan, and you say, okay, tangent theta. And you say, oh, root 3, that's on that row. What angle is it? Pi thirds. So that says theta equals pi over 3. All right, so progress has been made. And at this stage, we clean up. And there's a couple things that can happen. We can knock out a 3, knock out 1 secant. So we have then the following integral. This is going to be the integral 0 to pi over 3. We have 3 squared, that's 9, tangent squared, secant theta, d theta. All right. Okay, all right. I was thinking there might be a fraction, but nope, no fraction. So there we go. All right. Now, how do we integrate that? Well, this is going to be an interesting thing. How do we integrate that? Not nicely, to be honest with you, because what happens here? Oh, I know what happens here. Oh my gosh. I couldn't even copy it down right. See how it says x cubed? So this is a cube, not a square. I was panicking. It's like, no. It was like, oh, wait, good. This is why you double check your work. It's so easy to make a mistake. Okay, so it's not 9. It's 27. It's not tangent squared. It's tangent cubed. Crisis averted. Okay, so back to our regularly scheduled problem. How do we handle this? And you might say, I don't know, Steve, I feel pretty much like it's just the same before you corrected your mistake. What do you mean, how do we handle this? There is actually something. When you're faced with integrals involve secants and tangents, you ask yourself, can I pull off a secant squared and write everything else in terms of tangent? Or can I pull off a secant tangent and write everything in terms of secant? There's not a secant squared. So our only hope is to say, well, in that case, can we pull off a secant tangent? So we're going to do that, 0 to the power of 3. So we're going to have a tangent squared theta times tangent theta secant theta d theta. And what we'd like to be true, what would be really super duper convenient if it were true, is that this part, we want this to be our du. In order for that to be true, we need u to be secant. So we say, okay, is there a way to rewrite tangent squared in terms of secant? That's when we have that nice identity. Tangent squared plus 1 is secant squared. Or tangent squared is secant squared minus 1. Aha! Okay, all right. Now we're cooking. So we're going to make another round of substitution. That's like a double substitution. Is that allowed? Yes. We We can make as many substitutions as we want, although ideally we shouldn't have to make too many. The more substitutions we make, it's sort of like, did you not see a better path from the beginning? We still have our 27. All right, so let's update. Remember, these are theta bounds. We're going to have to update them to u bounds. We'll do that in a second. U is secant, so we have a u squared minus 1. And then the derivative of secant is secant tangent. That's why we pulled it off. Du. Now, our bounds. Secant of 0. So secant of 0 is 1. So there's a 1 there. And secant of pi thirds. Okay, well, that's go to your formula sheet and say, what is the value of secant of pi thirds? Well, it's not on there. But cosine is, and you flip the cosine. So what is cosine of pi thirds? The answer is cosine of pi thirds is a half. Flip it. Secant of pi thirds is 2. Nice. Nice. Okay. All right. So, integral 1 to 2. Okay, now we're in our home stretch. We have a very nice integral, and we are ready to say, well, this is 27. Then we get 1/3 u cubed minus u. Evaluate that from 1 to 2. So that's 27. We get 1/3 times 8 minus 2. Subtract 1/3 and then minus 1. All right, so we have 8/3, subtract 1/3, and that would give us what? That would give us a 7/3. So we have 27 times 7/3, and then we have a minus 2, minus 1. Well, okay, that's like minus 2 plus 1, which is minus 1. All right, so that's, well, multiply the 27 through, and we get 27 times 7/3 minus 27. 27 divided by 3 gives us 9. 9 times 7 is 63. 63 subtract 27 is a number. It's 36. So, there's the answer. 36. Whew! All right. We got there. We got there. Now, I think there's another way to do this. I think the people who wrote this test weren't paying attention. And here's the thing. They didn't tell us how we have to do it. So let's just look at the problem. Can you see another substitution? Let's try x squared plus 9. Okay, so we have the integral 0 to 3 root 3 x cubed over the square root x squared plus 9 dx. We'll let u equal x squared plus 9. And what is du? Well, 2x dx. Using my advanced marker technology, I'm going to move that 2 across. A half du is x dx. You're like, ooh, that's a pretty good marker, Steve. It is. It's a great marker. All right. And what do we have? Well, this will become integral. Substitute in. 0 squared plus 9, 9. 3 root 3 squared. Well, that's 9 times 3 is 27, plus 9 makes 36. What about this x cubed? Now, here's the fun thing. What's another way to think of x cubed? True story. X cubed is x squared times x. What is x squared? It's u minus 9. So this becomes u minus 9. That's the x squared. And then the x dx becomes a 1/2 du. And then what's downstairs? Square root of x squared plus 9 becomes square root of u. So this integral becomes what? Well, we'll bring the half in front. integral 9 to 36. Then we'll have u over square root of u is u to the 1/2 minus 9 over square root of u is u to the minus 1/2. And that's our integral. We don't need a second round of substitution. We're already in to our integration. So we get what? Well, this will become a 1/2 times, you add 1 to the exponent and divide. So that would be a 3/2 is a new exponent. Divide makes a 2/3. U to the 3/2. And then here you add 1 to the exponent, become a 1/2 divide. Well, how do you divide by a half? You multiply it by 2, minus 18 u to the 1/2. And evaluate from 9 to 36. And I think we'll almost make it. We'll almost make it. Okay, so I can multiply the 1/2 through. 1/2 times 2/3 makes 1/3. U to the 3/2 minus 9 u to the 1/2. And evaluate 9 to 36. When you plug in 36 to the 3/2 power. Now, I don't recommend taking 36 cubed and then taking the square root. Instead, take the square root of 36, which is 6, and then cube it. Well, that's 1/3 times 6 times 36. All right, that's the 36 to the 3/2. Minus 9 times square root of 36 is 6. And then we subtract from this, plug in 9. 9 to the 3/2, well, square root of 729. No. Square root of, it's the cubed of 3. So 1/3 times 3 times 9 minus 9 times square root of 9, which is 3. Okay, so 1/3 times 3 times 9, that one just becomes 9. Let's see, the 3 goes in here, so we have a 2 times 36. 2 times 36 makes 72. 9 times 6 minus 54. Subtract the 9, minus plus 27. And that makes 99. Subtract 63, which gives us 36. The same answer. So there's actually 2 ways this could have gone. Wow. Now, which one would give you points? The answer is they both would have given you points. Which one should you use? The answer, use what you're comfortable with. Use what you see. It's not so obvious how to do it. That's one of the things about integration, is there's not a single path. Sometimes you get to have a choose your own adventure. And so don't stress out about, I have to find the perfect way, or necessarily say, I have to find the way they want me to do it. You have to find a way. Find the way that works for you. This is your test. Make the most of it. All right. Well, now that we did that problem twice, let's how about we do the next problem just once. So number 8. Find the indefinite integral. So there's going to be a plus c at the end. So if nothing else, we're like, put something down, add a plus c, and we'll get a point. We're going to do more than just do that. What's our integral? X plus 1 over x minus 1, x squared plus 1 dx. What setting are we in? Well, here, there's no ambiguity. You see polynomial over polynomial. When you see polynomial over polynomial, then the only setting you're in is what we call partial fractions. All right, so that's where we're at. Partial fractions. So we are going to go off in that direction. So what do? Well, we're going to do a lot of algebra, and then at the end we'll do a little bit of calculus. And you might say, but wait a second, I thought this was a calculus class. Honestly, most of calculus is just a lot of algebra plus a little bit of calculus. And so that's why it's really important. Invest in your algebra. The more that you invest in your algebra, the better you'll be, the more points you'll get. And we like points. We are pro points. So, all right. So what's our algebra? Well, our algebra is to say we want to pull this apart. And it's a very common theme for integration. It says, if I have a lot of stuff, is there a way that I can pull it into lots of small, easy stuff? So instead of one big problem, a lot of smaller, easy problems. And so here, partial fraction says, if you have polynomial over polynomial, here's a way to help you pull it apart. So what we're going to do is we look at our denominator. The denominator clues us into how we're going to pull things apart. And we say, all right, well, what do we see down there? We see an x minus 1. So we say, okay, we're going to have something over x minus 1. And an x squared plus 1. So we say, all right, we're going to have something over x squared plus 1. Now, you might say, Steve, you use that word something very casually. Right, but what is it? We don't know. But we can say it's got to be a number over that x minus 1. And then it's going to be a bx plus c over that x squared plus 1. With a, b, and c to be determined. So that's really where we're going to go. So how do we determine these values? We start by saying, let's get rid of fractions. Fractions are dangerous, easy to make mistakes. So I'm going to multiply both sides by this x minus 1, x squared plus 1. When we do that, what do we have? We have an x plus 1. That's equal to a, all right, because we completely knocked out the fraction. Here, we just cancel the x minus 1 part, so that's an x squared plus 1, plus a bx plus c. Notice my generous use of parentheses. Parentheses are our friends. We like them. The x squared plus 1's cancel, and then we have an x minus 1. All right, so we need to find a, b, c. So there's a couple ways to do it, but I like to say make good choices. So are there some good choices that will help simplify the problem a lot? You know, the more we can simplify it, the better. Now, what makes something a good choice? Knock terms out. So notice here, if you plug in 1. So let's plug in x equals 1. We get 1 plus 1 makes 2 equals a times 1 plus 1, which is 2, plus this stuff times 0. Oh, well, hey, times 0, that's going to be 0. So that tells us, oh, good news, a is 1. Anything else? Well, now that we know a is 1, right, we can come here using our marker, put a equals 1. Is there any other choice that knocks something out? Well, you see how b is attached to x? Let's plug in x equals 0. Okay, 0 plus 1, 1, equals 1 times 0 plus 1, 1, plus c times minus 1. Okay, well, what does that tell us? Well, it tells us that negative c equals 0. Well, that's the same as saying c has to be 0. All right, great. So we know that this is a 0. All right, well, that just leaves us with b. And now, any value will do. So pick a number. Easy number. Well, let's pick negative 1. Why not? Easy to work with, relatively speaking. Negative 1 plus 1, 0. Negative 1 squared plus 1 is 2. So we have a times 1, 2. And then plus, we have a negative b plus 0, so that's a negative b. And a negative 1 minus 1 is a negative 2. So this becomes 2b. 2 plus 2b is 0. B is negative 1. Ha ha ha! Ho 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 ho! So, recapping, what is this shown? It shows us that x plus 1 over x minus 1, x squared plus 1, is equal to a 1 over x minus 1, bx plus c. So bx plus c makes a minus x over x squared plus 1. All right. Now that's the algebra interlude. So, right, we said we're going to do a lot of algebra and a little bit of calculus. So, how do we finish? Well, we finish by saying now that we've gotten that out of the way, the next thing to say is let's go back to our integral. And we're going to replace the inside part with what partial fraction says we can pull apart with. So we say, okay, our real integral is 1 over x minus 1 minus x over x squared plus 1. That's the real integral that we have to do. All right, well, the first one is not bad. That's a log of x minus 1. But what about the second one? Well, it's not an arctangent because the numerator is an x, not a 1. But now we say, what can we do? Well, we can do something really fancy and say this is like 2x over x squared plus 1, and then times it by a half in the front. You might say, wait, what? Oh, why'd you do that? Well, what I want to get to is function in the denominator, derivative in the numerator. When we see that, function downstairs, derivative upstairs, that's a signal that we have a log. And we say, okay, right? If you think about it, then what we've really said is like, set this part to be u. This part is your du. And the integral of 1 over u du is nice. So we have log of x minus 1 minus 1/2 log x squared plus 1. And there we go, right? Don't forget the plus c. Yes, even in Calc 2, we will take a point off if we forget the plus c. Nice. That's a good problem, good problem. And we didn't have to do it twice. Well, we didn't have to do that one twice either. Okay, number 9. Evaluate the improper integral. Ooh, most improper. We're going 1 to infinity, 1 over x log x squared dx, or show that it diverges. For full credit, you must. They even underlined it. They were like, you must use limit notation in your work. Well, we like full credit, so we're going to do that. Okay, so let's put our thinking caps on. We suspect this is an improper integral. And the reason we suspect it is because they told it to us. Now, why can things be improper? There's 2 ways something can be improper. One way is that you have an infinity involved in the bounds. Well, do we have that? Yes, we do have an infinity involved in the bounds. That says, okay, infinity is a problem. There's a second way. What's the second way something can be improper? Well, that's if there's an infinity in the function. The function blows up. Okay, so let's look at our function. And usually when we think about something blowing up, we think divide by 0. Well, if x equals 0, that's a problem, but 0 is before 1, so we don't have to worry about that. When is log x equals 0? Well, log of 1 is 0, so 1 is a problem. So that says, actually, we've got 2 problems. Double problems. What? Okay, so that's going to cause issues for us. All right, so we're going to make a quick note here. Improper at both endpoints. So that's going to be a concern. So what does that mean? Well, it really says we should split this into two integrals. So we're going to split the problem into two parts. Now, I'm writing this down. This is something you don't have to write down, but this is just something you realize, like, hey, I'm going to have to do that. Before we get into that, let's take an interlude. And let's talk about the integral of 1 over x log x quantity squared. Notice this is the indefinite integral. I just want to work that out on the side. Okay, so what can we do? I think this is one we can integrate. So when I'm thinking about integration here, I start thinking, well, is there a good substitution to make? I like the substitution. And I look for something on the inside. That log x, that's very tempting. That looks like it's on the inside of something. So let's do that. Let's let u equal log of x. Then du is 1 over x dx. And notice we have a 1 over x dx. So this becomes the integral of 1 over u squared du, or if you like, the integral of u to the minus 2 du, which add 1 to the exponent, minus 1 is the new exponent, and divided by minus 1, it's minus u to the minus 1 plus c, or again, u to the minus 1 is 1 over u, so 1 over log x, so minus 1 over log x plus c. Okay, so that's our intermission. Now, we said we're going to split it up. So here we go. We're going to say our integral from 1 to infinity of 1 over x log x squared dx. Well, pick a number from 1 to infinity. It can be any number you want. It can be 1,000,000, it can be 100, it can be 10, it can be 2. Just pick a number. Okay, I'll pick 5. So what we're going to do is we're going to think of this as the following. We're going to say, well, I'm going to write this as 1 to 5, 1 over x log x squared dx plus 5 to infinity. Again, this number 5 can be any number you want. Just pick a number. It doesn't matter. You're just splitting it into two parts. And now each one of these has its own problem. So we're going to say, okay, in the first one, this will be a limit as, let's say, a goes to 1 from above integral a to 5, 1 over x log x squared dx, plus the limit as b goes to infinity. Technically, we're going to infinity from below, but there's no other way. You can't be like, well, let me skip past infinity and let me come from above. That doesn't work. But integral 5 to b, 1 over x log x squared dx. Well, now we use our interlude. Say, hey, I know how to do these integrals. Each one of them is like a 1 over log x. And so, okay, this becomes the limit as a goes to 1 from above of minus 1 over log x, evaluate a to 5, plus the limit as b goes to infinity from below of minus 1 over log x, evaluate 5 up to b. Okay, now, our moment of truth. We're almost there. We have a minus 1 over log 5 plus 1 over log of a. Here we'll have a limit as b goes to infinity minus 1 over log b, and minus makes a plus 1 over log 5. But we go through and look at the terms. The 1 over log 5s, these are all good. So we are fine with those. Not surprising. 1 over log b, as b goes to infinity. Log of a big number gets big. It takes its time. It's not in a rush, but it gets big. So this part goes to 0 as a whole, this whole expression here. So we're happy with this part. Whoops. I put log 5. Log a. A's doing what? A's going to 1. Log of 1, 0. So this is going to 1 over 0. This blows up. So what does that mean? Well, it says this part diverges. So the limit, since, we'll even use words, since the limit as a approaches 1 from above, 1 over log a is infinity, the integral diverges. It doesn't matter that this second part is okay. Because no matter, even if this part is good, you can't make up for this first part. So it does diverge. So the integral diverges, right? Because we were asked to evaluate or show that it diverges. And because we got to this point where it says, hey, this first part, the part near 1, that part blows up, then it doesn't matter what happens with everything else. The whole thing must diverge. And so there we go. It blows up. And be careful with your notation, because they want to make sure you include your limits. It's, always know your limits, right? Absolutely. Absolutely. All right, that leaves us with one last problem. Number 10. Woohoo! Find the volume of the solid obtained by rotating the region. Okay, so there's a picture here because there's a region. All right, so we're above by y equals sine x, below by the x-axis, and x equals 0 to x equals pi. So sine x starts at 0 and comes back down. So here's 0, here's pi, and there's the x-axis. So that says our region is this piece. So there's our region. All right. And where are we rotating around? Make sure you pay attention. We're going around the y-axis. Okay, so we're ready to proceed. Now, because our curve is given to us as a function of x, by default, that's how we should think of this problem. We should think of it as saying, let's integrate with respect to x. So we're going to take a small little slice. Here's an x. And we're going to say, what happens if you spin that slice? What do we get? What do you see? This is a cylinder or a shell. So shell method. Okay, so we need to be using shell method. All right, so with that in mind, we look up and we say, well, how do you find volume by shell method? So you integrate a to b. There's a 2 pi, a radius, a height, and there's a thickness. So let's go through each one of these. First off, a and b. What are they? They are 0 to pi, because that's where our region goes from. So 0 up to pi. What's our radius? Well, the radius is from our slice to where we spin. So what's the distance from x to 0? Our radius is x. What's our height? It's this height from sine of x down to the axis. So the height is sine x. What's our thickness? The thickness is the thickness of this little slice, and that is dx. So we are trying to find the integral 0 to pi 2 pi x sine of x dx. All right, so there we have our problem laid out. Well, what's our tool? We see x, polynomial, and sine x, trig, in the same integral. So there's just one plan. This is integration by parts. And we say, okay, so good old integration by parts. How do we proceed? How do we make progress here? When we're doing integration by parts, there's sort of this mindset, like we have two pieces, and like, okay, we're going to take a derivative of one part, make it simpler, integral of another part, possibly make it more complex. We want to end up with something we can make progress on. Now, let's think about the candidates. We have x. Integrate x, you get x squared. That's worse. Differentiate, you get 1. That's better. Okay, so x is a good candidate for differentiation. What about sine of x? Integrate sine of x, and you get negative cosine. Differentiate sine of x, and you get positive cosine. So you're like, oh, it doesn't matter. So it's like, okay, go back to the x. And you say, okay, good. Now that we have that, this x, that's the part we want to differentiate. So if you think of integration by parts as integral of u dv is uv minus integral of v du, this is how it's often written, you say, well, I want the x to be my u and the sine x dx to be my dv. So then du is dx, and the integral of sine is negative cosine. Pay attention to your plus minuses. It's really easy to lose that when you have sines and cosines involved. So, updating. What do we have? I'm just going to switch colors here. It's time for a color change, right? You can't go too long in the same color. That would be confusing. uv 2 pi x minus cosine x, evaluate 0 to pi. We'll figure this out in just a minute. Subtract the integral v du. So minus a minus, so the minus can come actually out, and we get cosine of x dx and 0 to pi. Okay, so, well, good news is we can start evaluating. When we plug in pi, we get 2 times pi, cosine of pi, minus 1 times a minus times a 1. Subtract, plug in 0. 2 times pi times 0, and negative cosine of 0 is negative 1. But once you have it times a 0, hard to recover. And then, well, we should just note the integral 0 to pi of cosine. What is the integral of cosine? It is sine. Okay. And from 0 to pi. So we're going to add sine of pi, right? Plug in pi, and subtract sine of 0. But sine of pi is 0. Sine of 0 is 0. 2 pi times 0 times negative 1 is 0. So we have 2 times pi, leaving us with 2 pi squared, and that's the volume. And we're done. We reached the end of the exam, and we beat the 75-minute mark, right? Right? Well, barely. But hey, remember, we did one problem twice, so, all right. This is a tough exam. The one that we took is tough. The one that you're probably facing, let's not kid ourselves. There's a reason that this is a challenging class. So put in your time, put in your energy. You can do this. Maximize your points. Don't get stuck. Move on and come back. You can succeed. I believe in you. You are wonderful. Thanks for coming along and doing this with me. I hope you do well. All right. Bye.